Hello, Science 10, and welcome to our lessons on graphing. Today we're going to start by looking at distance time graphs. Your learning intentions, the why, is because we need to investigate uniform motion using graph analysis. So we're going to understand today how distance and velocity are related to each other using graphs. How are you going to do this is by identifying uniform motion when looking at a graph, and identifying an object, whether it's at rest, constant motion, or either forward or backwards, again, looking at a graph. And a key piece to all of this is finding the slope of a straight line. Now, sometimes our lines are not perfectly straight, so we're going to use a line of best fit. So today, distance versus time graphs or displacement versus time graphs. What we are going to do is I will post this video here on a separate part because it gives you a really good example of a distance time graph analysis in a broken down simplified form. But for us, we're going to skip it and we're going to go straight into graphing. Now, as a reminder, when we graph things, you have graphing paper in your note package. You need to include title, axes, as well as scales. We are going to look at the distance or displacement time graph first, and we are going to start with an exploration activity. So in your note package, you have these two sets of data. You can pause the video here and leave this up on your screen and use the graph paper to plot Alex's running data and Mike's running data. Now, please do it as a plot graph, so like dots. Do not do a bar graph. Do not do anything else, just little dots on your graph and create your graph. So pause video here and do that quickly. Now that you've created your graph should look something like this. Now you'll notice I created a legend for Mike and Alex so I know who is who. And I have a distance versus time of runners. So there's my title. I have my axes of distance and time, and they're with good scales that we can see that clearly use the space. Now you'll notice the data that I have on here is not in a straight line. So what we need to do is we need to do something called a line of best fit. And what that means is we are going to create a straight line through as many data points as possible. Now the goal is when we create that straight line is although we're not going to hit every dot, we want to have as many dots on the top as we do the bottom. So if you look at my blue line here, it's a straight line. Okay, but it runs through as many blue dots as possibly I could, as well as having dots on the top and bottom as many as possible. Same with my red one, okay, having some on the top and having some on the bottom. Now, what I also did is I found 2 points on my graph to help me create a triangle so I can do slope. All right. Now with a line of best fit, you'll notice my blue line here doesn't start at the origin, and that is okay. My line of best fit doesn't have to start at 0. I'm just creating a straight line through as many data points as I possibly can. Now on my graph, you'll notice I have picked a couple of different places. So for Mike here, I have this at 6.6 and 1.2 and 17.4 and 2.6. So the idea here is I could connect these two and I would do what we call rise, which is up, over run, which is across. And so what we're going to do is we are going to calculate Mike and Alex's slopes to see what their velocity is. What we are going to do is we are going to take them and we are going to start by finding the difference between 6.6 and 17.4. So I'm going to take 17.4 and I'm going to subtract it from 6.6. That is the difference or the run of my graph. So that's the time value, and I get 10.8. I'm going to take 2.6 and I'm going to minus 1.2, and I get 1.4. And that's the rise of my graph or the up part of my graph. So now, in order to calculate slope, you're going to take rise and you're going to divide it by run. So I'm going to go 1.4 divided by 10.8, and I get 0.1. I'm going to do the same thing for Alex, okay? And I'm going to use my 2 data points here. I'm going to create a rise over run, and I am going to then figure out my slope. So my slope ends up being my speed, because we learned that speed is distance over time, or velocity is displacement over time. So these graphs allow us to see the actual speed or velocity that each of the individuals went. Now, Mike actually ran 0.12 kilometers per minute, and Alex ran 0.1 kilometers per minute. So Mike was a little bit faster, which makes sense because if we look at our graph, my line shows just a little bit of a more of a slope than my red line. Therefore, we know that Mike ran just a little bit faster than Alex. So when we are looking at distance versus times graphs, the idea is to interpret them and understand what's happening. So you can see line 1, 2, 3 here. Car 1 is actually traveling faster than car 2 because our slope, which is rise over run, is steeper. And our second car is traveling at a constant speed as well, but it's a little bit slower than car 1. Ultimately, all of the cars, okay, are doing some sort of movement except for car 3. Car 3 has no slope. Therefore, there is zero speed happening in car 3. So here, pause the video and in your notes, add to this what you have here. You'll notice I highlighted some key pieces, such as this distance time graph is at rest, where this distance time graph is showing constant speed. This distance time graph is showing constant speed, but the dotted line is at a higher speed than the solid line. Over here, we have acceleration, and we haven't looked at acceleration in graphing yet, and that's okay, but can you still record what you're seeing there? Because you'll notice acceleration has a curve to the line. It is not showing constant motion. This is showing constant motion when something is moving back. So ultimately, in the end, we can put it all together and look at a graph to understand how things are moving. So this is my displacement versus time. And if I was to figure out the slope, I would know velocity. So this is a nice fast and steady speed. We can see that based off of the line itself. If I had numbers on here, I would be able to do my rise, how high up I go, and how far across I go is run. I would actually be able to figure out the velocity of this vehicle compared to this vehicle. And although I already know, based off of what I see, that this one is faster than this one, I can prove it quantitatively by using displacement over time. And that's what's showing up here, is this is just showing my slope is displacement over time, and that will give me my velocity. Here, I can see a car moved at a constant speed, stopped, sat for a while, and then returned to its start position in a steady speed. So this again is showing me my displacement. My vehicle didn't travel anywhere, started at the same place I was originally, but I'm able to figure out how much velocity was happening during these two spaces. And I know because nothing was going on here, it wasn't moving, time was passing, but no distance was covered, that at that moment in time, there was zero velocity. So that's it for our displacement versus time graph.